This is, we'll go over test 2 now. The first question asked you to find whether sequences converged or not. These are not series, it's sequences, just an infinite list of numbers. And you want to know if, as you go far out in the list, if all of the terms of the sequence become essentially, well, arbitrarily close to one number. So in the first example, we see cosine k, and that being our numerator is a good candidate for the squeeze theorem because it doesn't remain stable. It's always going between -1 and 1. So we write -1 less than or equal to cosine k less than or equal to 1, and then divide through by the denominator, which is positive, so the inequality signs remain in the same direction. And then you see that the left term has a denominator that's blowing up, a numerator that's constant, so it goes to 0. Same on the right hand side. So we have the limit of a sub k as k approaches infinity is equal to 0. Or you can write just a sub k arrow 0. The second part, b sub n, is the natural log of n squared over n cubed plus 1. Well, if this were in the inside of another problem, I wouldn't mind if you just said, I know this goes to 0 because the n cubed is growing at a much faster rate than natural log n. But this asks you to determine the limit, so that means that you should prove that the limit is 0. And we would do that by using L'Hopital's rule. Natural log n is always a good candidate for L'Hopital's rule because when we take the derivative of the top, but first notice, the top is becoming infinite and the bottom is becoming large without bound. Therefore, we can use L'Hopital's rule. So, we take the derivative of the top, 2 natural log n times the derivative of natural log n, 1 over n, over 3n squared. Simplify. You'd have to use the product rule. In fact, you have to simplify this before you see if you can use L'Hopital's rule again, or possibly you have the answer. This would be 2 natural log n, and the 1 over n, well, the n just comes down into the denominator as a factor, and you have 3n cubed. Well, again, the top is still getting large without bound, so is the bottom, so we use L'Hopital's rule again. Let's put LR whenever we use it. Okay, so we take the derivative of the top, 2 times 1 over n, over the derivative of the bottom, 9n squared. Again, the 1 over n, that's the same thing. Let me show you. It's the same thing as 2 over n squared times 1 over n. That's why the n comes down, and you have 2 over 9n cubed. Well, now you have the bottom becoming infinite, and the top is just a number, so we can say arrow 0. Here we have a sum on the top and a sum on the bottom. So I think we should take the most powerful thing. Certainly k factorial beats any power of k. So let's divide by the most powerful term on the top and on the bottom. So we have k to the 10th over k factorial plus 1, k factorial over k factorial. And the bottom becomes 3 over k factorial minus 8 k factorial over k factorial. Okay, so now this is what I mean. You can go ahead and say that this goes to 0 because we've proven in class that using L'Hopital's rule 10 times, we couldn't use L'Hopital's rule with k factorial. This is when we wrote out and we took out factors that were less than 1. And you can look back in your notes and see that we proved that a power of k over k factorial goes to 0. And I'm not asking you to prove that, so you can just use it. 3 over k factorial goes to 0. So this limit is -1/8. part in there. So we're starting D over again. Again, I want to look at the argument here. And if you look at well, let me write it, the cube root of n plus 3 over 4n cubed plus n plus 2. Okay, you could ignore the 3, and this is n to the 1/3, and this down here is n cubed, so we know that n cubed is the most powerful. So I'm going to divide by that. The cube root of n plus 3 divided by n cubed over, and now dividing each term by n cubed, 4 plus 1 over n squared plus 2 over n cubed. Now look at this. N cubed, I want to bring it up under the cube root. So I'm going to think of n cubed as the cube root of n to the 9th. And we get then the cube root of n over n to the 9th, 1 over n to the 8th, plus 3 over n to the 9th, over 4 plus 1 over n squared, plus 2 over n cubed. So we see that the bottom denominator goes to 4, and the numerator goes to 0 as n goes to infinity. So we can say that this argument goes to 0. So you think of the natural log function, looks like this, and as these are all positive numbers, so as the argument of the natural log goes to 0 through positive values, we see that the natural log is approaching minus infinity. So this has no limit. We would say that the limit does not exist. So now we're going to test series for convergence and divergence. Notice that this is not a power series. There's no x in here. This is just the sum of the terms of a sequence, and we're seeing if the sequence of partial sums converges. So we can't see a formula for the partial sums, so we use different tests that we learned in Calc 2. The comparison test, the ratio test, the integral test, and the test for divergence. Well, first we do notice that the denominator is growing faster than the numerator. This nth term or kth term will go to 0. So we need to test the series for convergence. I think when you just have powers of k on the top and on the bottom, a p-series to compare to is what you want. So you think, well, here I just have k to the 1/2, and this is k squared. So the comparison series that I hope to compare it to is this one. And just throwing everything out except what really counts. And this is k to the 1/2, so that is sigma 1 over k to the 3/2, which we know converges. So this would be our comparison series. So let's take our kth term, 5 plus 2 times the square root of k over k squared. We want to compare it to that, but I can't throw out the 5 and I can't get this less than 1 over k to the 3/2. So the comparison test won't work. The limit comparison test would work nicely here, and we would use that as our comparison series. I could also make this work like I showed you in class the other day, but I think the easiest thing to do here is to just split it apart. If I was to make this work, I have to get this less than some constant times that. So I could do that because I could say, well, after k is 25, 5 is less than the square root of k plus 2 times the square root of k over k squared. if k is greater than 25, and we're only concerned with large values of k, and that is equal to 3k to the 1/2 over k squared, which is equal to 3 over k to the 3/2, and sigma 3 over k to the 3/2 converges. K is greater than 1, so therefore our series here will converge by the comparison test. But I don't think most of you would have thought of how to grow this fraction. It's a little bit complicated, so let me show you a simpler way. I just didn't think of it when I was doing it, looking at this. Let's just split. This is the sum of 5 over k squared plus the sum of 2 times the square root of k over k squared, which is k to the 3/2. Now, since both of these series are convergent p-series, we can split this up into the sum of these two series. They both converge, so we know that the one that we started with converges. That's definitely the easiest way to do this one. The next one, we have the most powerful thing there is 3 to the k on the kth term. So we could compare this to a k-series or a p-series. Here, I'll do it both ways. We could say that 9 over 3 to the k plus k cubed. Now I want to make it bigger, so I could make it bigger by making the denominator smaller. I could write 9 over 3 to the k, and summation 9 times 1/3 to the k converges. R, the absolute value of r, is less than 1. Therefore, the series will converge. Another thing you could have done in this case is 9 over 3 to the k plus k cubed is less than 9 over k cubed. We could have thrown out the most powerful thing down there and still gotten a convergent series. And summation 9 times 1 over k cubed converges. P is equal to 3. P is greater than 1. So you could have compared it either to a convergent geometric series or a convergent p-series. Part C, we see that always check, this one will check for test for divergence. If you look at the argument of the natural log here, it's going to 0. And so the natural log is going to minus infinity. So a sub n, the nth term of the sequence, is not going to 0. Therefore, the series diverges. The series diverges by the test for divergence. I should put, therefore, I should put it in, or you should, sigma natural log of 1 over n plus 1. The series diverges. The next one is still just a regular series here. I guess this one wasn't on your test, but I put it on as an example that would be likely on the final. This one is a candidate for, well, it's all factors on the top, factors on the bottom. We see factorials and exponentials, probably the ratio test. Now, the ratio test is a test that looks at the limit of the absolute value of a sub n plus 1 over a sub n. So we have to take absolute value. Remember, when you take the absolute value of a power of -1, it's just 1. So we can just write k plus 1 to the 10th over k plus 1 factorial, and that's over this. So I'll invert and multiply k factorial over k to the 10th. And I would look at this as k plus 1 to the 10th over k to the 10th is k plus 1 over k to the 10th times k factorial over k plus 1 factorial is 1 over k plus 1, canceling the k factorial. Well, the inside of this that's being raised to the 10th power, k over k plus 1 obviously is converging to 1, and 1 to the 10th is 1. This 1 over k plus 1 is going to 0. So the limit is 1 times 0 equals 0. So this series converges by the ratio test. We came out with a limit which was less than 1. Therefore, the series converges. Number 5, you're asked to use the integral test. On the final, I would tell you to use the integral test. So we know that we're going to be looking at the limit from 1 to infinity of, and write this out as e to the 1 over x times, well, that's 1 over x squared dx. And that will be equal to the limit. Every step that you write, if it's proper notation and using your definitions, you get partial credit. The limit as t approaches infinity of the integral from 1 to t of e to the 1 over x times, well, I'm going to put minus 1 over x squared dx and adjust with a minus 1. You can bring the constant out to the left of the integral or all the way out to the left of the limit. Why did I do that? Well, because this is e to the u du. So we can just integrate. We don't have to ever really write in the u. Let me go to white here. You can see it better. So we have minus the limit as t approaches infinity. E to the u du. The integral is e to the u. So it is e to the 1 over x evaluated between t and 1. So we have minus the limit as t approaches infinity of e to the 1 over t minus e to the 1 over 1. E to the 1 is e. All right, now 1 over t goes to 0. We finally are taking the limit. 1 over t goes to 0, and e to the 0 is 1. So we have a limit here. Minus 1 minus e, or e minus 1. Now you don't actually have to write e minus 1. You could just say that this limit, once you see that goes to 0, this is a finite limit. Therefore, the series converges by the integral test. Remember, when you're using the integral test, the series converges or diverges the same as the integral does.